Hello everyone, welcome back to Altium Academy. I'm your host, Zach Peterson. Today we're going to be doing a little follow-up video to our recent video about decoupling capacitor placement and why it is less important when you're using planes versus using traces. Now this follow-up video was all spawned by a message I received from a viewer through LinkedIn. And this message specifically concerns the use of traces versus vias to make connections to power and ground nets when placing and connecting decoupling capacitors to integrated circuits. As we go through this question, we're going to take a look at some examples in Altium Designer, and we're going to see what real pinouts look like and how they can sometimes constrain capacitor placement and force you to use one connection type over the other. Let's go ahead and jump in and get started. Now this video is a great follow-up to our previous video about decoupling capacitor placement and whether or not it is really sensitive to location when you're using planes to route power and ground into an integrated circuit, particularly a large integrated circuit that uses a BGA package. Now, if you haven't watched that video, make sure to check out the video link in the description and go watch that video before we continue here. Now, if you have watched that video, you'll know that we arrived at two important conclusions about the location of decoupling capacitors around large integrated circuits. The first is that if you have a BGA package and you have to use power planes and ground planes to route power into that BGA, the location of the decoupling capacitor is less important when the planes are very large. That's because the connection between the decoupling capacitor and that BGA has very low inductance, and it's much lower inductance than if you were to use traces to connect the pads of the decoupling capacitor into the pins on the BGA. But the second thing that we saw, which is much more important, is that when we have a BGA package, it's generally impossible to make that connection using traces because the power and ground pins tend to be clustered in the center of the BGA package rather than around the edge. Now, in that situation where you have a package where the leads are located around the edge of the package, it is possible to bring a decoupling capacitor very close to the leads and make the trace connection. But what we didn't address in that other video was how we make the connection back to the power and ground net in the PCB. Should we use vias and connect directly to the power and ground planes? What if we don't have a power plane and we only have a ground plane? Should we just use a long trace routing over to the power net? These are all important questions that we didn't address in the other video, and they came up recently in this LinkedIn question that was sent to me by Peter Barnes. Let's take a look at Peter's LinkedIn question. Peter writes, "Hi Zach, I was at a Worth/Analog Devices seminar the other day, and the FAE from Analog Devices referenced his comment on this LinkedIn post." And here he gives us the link to that LinkedIn comment. "I did my best to convince him at the time that you are better off with a ground via for every decoupling capacitor and solid reference planes, but I don't think I managed to change his mind. He was also recommending analog ground islands under DC-DC converters, which I know for sure is a bad idea." Well, Peter, you are absolutely correct about that. Perhaps you could reply to his comment. He does say that he would welcome a good argument. Well, you all know I like to argue with people on LinkedIn, but sometimes it's more fun to start the argument on YouTube. So before we go further, let's take a look at this post and comment. So this post came up from Omar Farouk Demirtas. Here he's showing what happens when you place a decoupling capacitor and then make some connections back to the power nets. He details a correct way to do it and an incorrect way to do it. In reality, they're both incorrect because he's placing ferrite beads on the power nets, but let's just ignore that for the moment because I've explained that one to death. Let's just focus on the placement of the decoupling capacitor on the positive voltage net and then the ground pin over here on the bottom side of the IC. So basically what Omer is saying is that the correct way to do this is to use individual vias on the ground pin and then on the grounded pad on the decoupling capacitor. Whereas the incorrect way to do this would be to route this long trace from the decoupling capacitor pad over to this via and then share that via between the decoupling capacitor net and this ground pin on the IC. Now the comment Peter Barnes is referencing is right here from Simon Bramble. And Simon writes, I am not so sure this is correct. A PCB trace generally has a lower inductance than a PCB via, and you need to keep the inductance low to maintain the high frequency performance of the capacitor. A PCB trace has a return path through the ground plane, which keeps its inductance pin small unless the ground plane is several layers below the trace. In addition, you are decoupling the whole device, not just the V+ pin. The power supply that the device sees is the one between its V+ and ground pins, so it is this voltage that needs to be decoupled, not V+ to any local ground node that might be at a different potential to the ground pin. So we're going to investigate Simon's statements just a little bit inside of Altium Designer by looking at a couple of real components and the location of their power and ground pins, and then we can understand a little bit better what are the optimal ways to make those connections. Because sometimes it's not just about the inductance, it's actually about what type of connection method is practical given the location of those pins on the integrated circuit. Now, before we investigate these statements from Simon Bramble, what I want to do is take a look at a couple of real components that have the leads exposed around the edge of the package and with the power and ground pins in different locations. This is going to help us see how we might have to place and route the connections from the decoupling capacitor into those power and ground pins based on the location of those pins in the package. So here I have our Ethernet switch project pulled up, and we're going to look at two memories that we have placed in this design. And if you're interested in learning more about this design, you can go and access the design files from the link in the description. You can also see a link to a video where we go over the design for this Ethernet switch. So here we're going to look at the SPI boot flash, and you can see here we have a power pin and a ground pin. So we have a single power pin, single ground pin on pin 2 and pin 10. And then we're also going to look at the NAND flash. This NAND flash has 2 power pins and 2 ground pins, and you can see that we have a decoupling capacitor right here linking them. So now let's take a look at these packages in the PCB layout. Here you can see we have the larger NAND flash, and then that one decoupling capacitor is located right here. And then here we have the smaller SPI boot flash, and then it also has a decoupling capacitor, which is located right here between pin 2 and ground. So first, let's look at the smaller SPI flash. So here on this SPI flash, you can see here that we have our power pin right here on pin 2, and then we have our ground pin all the way over here on pin 10. So they're on opposite sides of the package. Now, if we just go back over here to this post on LinkedIn, and then we just scroll up here to the image from Omer, this situation looks a lot like the image on the left, where we have a lot of distance in between the power pin and the ground pin. Now here, Omer says that the correct way to do this is to put a via to the ground plane right here on the ground pin, and then put a via to the ground plane right here on the negative side of this decoupling capacitor. Now here in the PCB layout, you'll see that we do have a via going into the ground plane, but then we also have a via going into the power plane. So the question is it better to place these vias connecting to the planes rather than routing a trace from the ground pin on the capacitor all the way over here to this ground pin on the integrated circuit? Well, I think the answer is obviously yes. This is clearly better. It's better just from a placement and routing perspective. Why would you route a big trace all the way up here and take up all that space when you have a convenient connection to ground through a via, both on this pin and on this pin on the decoupling capacitor? So to me, it seems obvious that when you have the power pin and the ground pin placed far away from each other, the optimal way to do this in terms of convenience of routing is to just use vias to connect back to the plane. Now let's go back and take a look at Simon Bramble's statement here in the comments. So Simon Bramble says that I am not so sure this is correct. A PCB trace generally has a lower inductance than a PCB via, and you need to keep the inductance low to maintain the high frequency performance of the capacitor. Well, what we saw in our earlier video on decoupling capacitor placement was that it is true. You do need to keep the inductance low to maintain the high frequency performance of the capacitor, just like Simon says right here in this sentence. So that is a true statement. What is not a true statement is this part of the sentence, which is that a PCB trace generally has a lower inductance than the PCB via. That is actually not true. It is only true when traces are very short. And the reason is that traces have an inductance per unit length. We can actually calculate what that inductance per unit length is inside the layer stack manager inside Altium. So here inside the layer stack manager, you can see that we have the impedance tab brought up, and over here on the right hand side, we can see that we have an impedance calculation, and it gives us the inductance per unit length. And you can see here that the inductance of this 6.1 mil trace, which is a 50 ohm trace for a DK4 laminate, is 7.85 nanohenries per inch. Now, just a rough estimate of the distance in between this power pin and this ground pin is about 1/2 inch. So this would be about a 3.9 nanohenry connection just between this capacitor and this ground pin on this integrated circuit. Well, that 3.9 nanohenries is about 4 times as large as a typical PCB via that would connect back to the ground plane. So clearly, in this case where you have the power pin and the ground pin at a very large distance from each other, using a trace is not optimal from the inductance perspective as well as from the routing convenience perspective. That trace connection is always going to have a higher inductance than the via connection back to that plane, and that's why in this situation with this type of chip on screen, we would prefer to always use the vias to make the connection back to the planes rather than routing a big trace all the way from the decoupling capacitor pin over to the integrated circuit pin. Now let's take a look at the other memory that we have in this design. So you can see that this chip is right here. We have a decoupling capacitor placed right here in between the power pin and the ground pin. So you can see very clearly the power pin and the ground pin are right next to each other. Now, it's worth asking, in this case, is it better to route traces directly from the capacitor to the pins? Or instead of using these traces, should we then also just put a via right here that connects from the internal plane directly to the pins? So for example, should we do something like this with the 3.3 volt net? And then should we also do something like this with the ground net? Well, here in this connection where I've just quickly placed these vias on the 3.3 volt net and the ground net, we have a via going from the 3.3 volt pin into the plane and then coming back up through another via and then going into the pin. So that's approximately 2 nanohenries of inductance from those two vias. I haven't included the trace impedance because, as you can see here, the traces are very short, only about 1 millimeter in length. Same thing here for the ground connection. We'd have 1 nanohenry of inductance here from this via and approximately another nanohenry of inductance from this via. However, if we just make the connection using the traces as we had originally, we would have much lower inductance. Here you can see that we would have a distance of about 70 mil. So that's a much lower inductance connection when we can route these traces directly from the decoupling capacitor over to these pins. The only reason we're able to get such a low inductance connection in this case is because the power and ground pins are literally right next to each other. And that's what allows us to place that decoupling capacitor very close and route in with these very short traces. So to summarize, should you use traces on every pin or should you use vias on every pin to make connections between decoupling capacitor pins and integrated circuit power and ground pins? Well, it depends. Where are the pins located? How far apart are they? Are they located right next to each other, and can you bring that decoupling capacitor very close and make those trace connections? Those are the types of questions that you need to ask. And unfortunately, that context is not clear if you just take a look at the image provided by Omer on that LinkedIn post. Hopefully this adds just the right context that you need to understand decoupling capacitor placement and power integrity, specifically in the case of integrated circuit packages where the leads are located around the edge of the package. Thanks for watching this video, everybody, and of course, don't be afraid to send me your questions on LinkedIn, or of course, you can hop into the comment section and leave your comments and questions there. Don't forget to subscribe to the channel, and don't forget to call your fabricator, folks. We'll see you next time.